Welcome to the deep dive. Today, we're jumping into, well, a really critical area for anyone deploying LLMs, making them smaller without breaking them.
That's the challenge, isn't it?
Absolutely. Our source is a paper on an approach called SINQ. That's SINQ, Sinkhorn Normalized Quantization. It's all about post-training quantization, PTQ.
And specifically, tackling the quality problem.
Yeah.
When you push these models down below, say, 4 bits using the simple methods.
The calibration-free uniform methods, the ones we'd ideally like to use because they're fast and simple.
Right. BTQ is basically essential for deployment now. Everyone knows that.
Yeah.
But the easy way, the calibration-free uniform way, just hasn't cut it for quality at those really low bit widths.
So this paper, SINQ, is trying to bridge that gap, make the simple method perform like the complex ones.
That's the goal. They argue they can do it with a pretty clever transformation of the weights before quantization. It's not about adding complex calibration data or anything like that.
Okay, interesting. So what are the key pieces they introduce?
3 main things, really. First, they change how weights are parameterized using what they call dual scaling. Think 2 scale factors instead of 1.
Okay, 2 factors.
Second, they define a new metric to optimize for, called matrix imbalance. It's a proxy for how easy the weights will be to quantize after transformation.
Matrix imbalance.
Yeah.
And the third?
A fast algorithm to actually do the transformation. It's based on the classic Sinkhorn NOP algorithm, but adapted for this imbalance metric. It's designed to be super quick.
So dual scales, matrix imbalance, and a fast Sinkhorn-style algorithm. A complete package for better, simple PTQ.
That's the idea. Aiming for top quality within the simplest framework.
Okay, let's maybe take a step back first. Why are we so focused on making uniform, calibration-free quantization work well? Why not just accept that we need calibration like in EWQ or GPTQ or non-uniform formats like NF4? They already give better results at low bits, right?
They often do, yeah, but it comes at a cost. And that cost really matters in practice, especially at scale.
Okay, break down those costs for us. Let's start with calibration.
Calibration means you need data. You have to run maybe a few thousand examples through the model just to figure out the right quantization parameters like scales or shifts.
Which takes time.
It takes compute time, definitely. But it's more than that. There's a risk, as some studies have pointed out, that you might actually overfit to your calibration data set.
So if your calibration data isn't perfectly representative of real-world traffic?
Your quantization might actually be suboptimal or even biased. Plus, imagine managing that calibration process across hundreds or thousands of deployed models. It's a significant operational overhead.
Right. Calibration-free avoids all that.
Right.
It's just apply the math, done.
Exactly.
Yeah.
Instantaneous, robust to data shifts, much simpler operationally.
Okay, that makes sense for calibration. What about non-uniform formats then? Things like NF4, they don't need calibration in the same way, but they handle outliers better inherently.
They do handle outliers better because the quantization levels aren't evenly spaced. But the trade-off there is often inference complexity. Well, formats like NF4 typically require lookup tables during inference to convert the stored quantized value back to its actual representation. That lookup isn't free computationally.
Okay, adds a bit of latency or complexity to the hardware path.
Right. And maybe more critically, if you're in a situation where you're really pushing the hardware, maybe trying to quantize both weights and activations.
Which you might need to do for maximum speed up.
Exactly. The added complexity of non-uniform weight formats can sometimes make it harder or less efficient to combine with other optimizations like activation quantization. You might hit a complexity wall.
So the dream scenario is getting uniform INT4, the simplest, most hardware-friendly format, to work just as well without needing calibration or lookup tables.
That's the holy grail, really. If simple, uncalibrated uniform INT4 can match the quality, it becomes the default choice for pretty much everyone, simplifying hardware and software stacks enormously.
But it hasn't matched the quality so far, especially below 4 bits. And the reason you mentioned is outliers. Let's dive into that specific problem.
Yeah, the outlier issue is fundamental. In these huge LLM weight matrices, most values are tiny, clustered near 0.
Right. It's a very peaked distribution.
Very peak. But then you have these occasional scattered values that are orders of magnitude larger, the outliers.
Oh, yeah?
Now, with uniform quantization, you typically group weights together, maybe a whole row or a block, like 128 by 128, and assign a single scale factor to that entire group.
And that scale factor has to accommodate the biggest value in the group.
Precisely. It has to be large enough so that the outlier, when scaled down, still fits within your, say, 4-bit range, -8, 7.
I see the problem. If one value is huge, the scale factor becomes huge.
And then all the other values in that group, the typical small ones, get squashed into just one or two quantization levels when they're scaled down by that same huge factor.
You lose all precision for the common values.
You basically obliterate their information content. It's like turning most of your weights into noise. And that's why performance tanks. One outlier poisons the scale for potentially hundreds or thousands of other weights.
The tyranny of the maximum value, as you put it earlier.
Exactly. And we need to fix this for weights, specifically because weight memory is often the first bottleneck we hit. Moving weights takes time and energy.
Right. Memory bandwidth and capacity.
Yeah. If you can shrink weights from, say, bfloat 16 down to INT4, that's a 4x reduction in memory footprint. In memory-bound scenarios, that could directly translate to a 4x speedup.
Huge potential.
Massive. So finding a way to get that 4x memory saving without wrecking the quality, without complex calibration, is incredibly valuable. That's what SINQ is trying to unlock.
Okay, problem clear. Outliers ruin uniform scaling. SINQ's first innovation to tackle this is the dual scaling parameterization. Let's unpack that. How does it differ from standard PTQ?
So standard uniform quantization, the baseline, approximates the weight matrix of dollars. Let's call the quantized integer matrix extruder. The approximation we'll prox is usually something like VEC plus VESQ.
Where dollars is element-wise multiplication.
Right. And VEX and VEC is a scale vector. VEX is an optional shift or 0-point vector. Crucially, VEX and VEX are typically 1D vectors. They act along one dimension, say scaling each row independently, or maybe scaling blocks of weights.
So one scale factor per row or per block, still vulnerable to the outlier within that row or block.
Exactly. That's the constraint. SINQ breaks that constraint by introducing two scale vectors. They propose an approximation like 1xm vex.
Okay, wait. So vexes might be, say, n by 1, scaling the rows.
And vexes would be, say, 1xm scaling the columns.
Ah, so the quantized value qi gets scaled by both sextant and tester.
Correct. Every element is influenced by both a row scale and a column scale simultaneously.
Okay, let's think through why that helps with an outlier. Let's say 1 is there's that massive value again.
Right. In the old way, 1i forces Zuminal, the scale for its entire row, to be huge. Lots of error across row dies.
But now?
Now, you have two knobs. You can still increase the row scale error day dollar to help represent nj, but you can also adjust the column scale tj day. Maybe you decrease tj lightly.
So you're saying the effective scaling dollar is now shared between $6 and TJ. You can trade off the error.
That's the core insight. You can distribute the burden of representing that outlier across both the row and the column dimension. You're not forced to dump all the scaling error onto just the row scale or just the column scale.
That sounds much more flexible. You're preventing the error from concentrating along one line.
Exactly. You're managing the variance, managing the error distribution. With a single scale, the row and column effects are coupled. With two scales, they're decoupled, giving you this crucial control. It's fundamentally impossible with single-scale methods.
Okay, that makes intuitive sense. But the immediate question is overhead. We just added a whole extra scale vector. Doesn't that increase the amount of extra data we need to store alongside the quantized weights? We wanted simplicity.
That's a very fair question, and they thought about it. If you just naively added a full n by 1 vector Delis Neuer and a full 1xm vector tout for the whole matrix, yes, the overhead could be significant.
So how do they manage it? Tiling.
Tiling is key. Remember, standard methods also use tiling, often 1D rectangular tiles like n rows by t columns, where t might be 128 or 256. The number of scales and shifts is roughly $2 n times mt2.
Okay.
To keep the parameter count similar with dual scales, SINQ proposes two main options. One is to switch to 2D square tiling using TXT blocks. If you do the math, using TXT blocks with dual scales keeps the number of auxiliary parameters roughly in the same ballpark as 1D tiling with single scales plus shifts.
Square tiling.
Okay?
Okay. But is that always the best for hardware? Rectangular seems common.
Right. And that leads to their second and perhaps more practical option, which they use a lot in the paper. Stick with 1D rectangular tiling, but use the full parameterization, dual scales plus shifts.
So that looks like 1DisQ plus vex.
Exactly. Here, Vickers might be tiled like usual, 1 per NXT block, but VEC is kept as a full 1xm vector, 1 scale per column.
So the overhead compared to standard 1D tiling with scales and shifts is just that extra vector.
Essentially, yes. The total auxiliary parameters become $2 times n times mt2 from Vevison into account store. It's a very modest increase in parameters.
And the argument is that the quality improvement from having that full column-wise control vector justifies that small extra cost.
That's exactly the argument, and the results seem to bear it out. That extra vector gives you fine-grained control across the columns, which complements the blockwise row scaling.
Okay, we have the mechanism. Dual scaling, possibly with shifts, using tiling to manage overhead. But how do we find the right values for vector to vector? We need an objective. This brings us to the matrix imbalance metric.
Right. The goal of dual scaling is to balance the impact of outliers, to make the weight distribution look more uniform from a variance perspective along both rows and columns. So the metric they define, IW to ball, captures exactly that.
How is it defined?
It's simple conceptually. IW is the ratio of the maximum standard deviation found across all rows and all columns, divided by the minimum standard deviation found across all rows and all columns.
Max standard deviation over min standard deviation.
Yep.
Okay, so if all rows and columns had the exact same standard deviation.
The ratio 1:1 would be 1. That's the ideal state of balance. A high imbalance means some rows or columns have vastly larger variance than others, indicating outliers haven't been properly absorbed by the scales.
So the optimization goal is simple. Find the scale factors FAO die that minimize this imbalance ratio IW dollars.
Precisely. Make the matrix look as balanced as possible in terms of variance distribution.
But optimizing this directly sounds tricky. Max and min operations, they don't play nicely with standard gradient descent, do they? The gradients are often 0 or undefined.
Exactly. That's the snag. The non-smoothness makes gradient-based optimization inconvenient. So instead, they drew inspiration from a classic numerical method.
The Sinkhorn NOP algorithm, you mentioned it earlier. What's the connection?
The original Sinkhorn NOP algorithm from the 60s is this neat iterative process. You start with a non-negative matrix, and you alternate between normalizing its row sums to 1 and normalizing its column sums to 1. You repeat this, and it converges to a matrix where all row and column sums are 1, a doubly stochastic matrix.
Okay, normalizing sums. But here we care about standard deviations variances.
Right. So SINQ adapts the iterative alternating normalization idea. Instead of normalizing sums, they normalize standard deviations.
Ah, okay. So walk us through their algorithm 1, the SINQ process. How does it work iteratively?
It's surprisingly straightforward. First, you calculate the standard deviation of every row and every column in the original weight matrix dollars. You find the overall minimum standard deviation among all of these, let's call it sigma min. The sigma min becomes the target standard deviation you want everything to converge towards.
Okay, establish the target floor.
Then you iterate. In one step, you calculate the current standard deviation of all the columns. You then divide each row of the matrix by these column standard deviations. But crucially, you clip the standard deviations first, making sure you don't divide by anything smaller than sigma min.
Okay, normalize rows based on column stats. Then you flip it.
Exactly. In the next step, you calculate the current standard deviation of all the rows. You then divide each column by these row standard deviations, again, clipped at sigma.
And you just keep alternating. Row normalization based on column stats, then column normalization based on row stats.
You keep alternating. Yes, it's like you're constantly pushing the variance down. If a row has high variance, you scale it down. But that affects the column variances, so in the next step, you scale down the high variance columns. It's this back and forth that drives the whole matrix towards a state where all row and column standard deviations are close to sigma min.
And the scale factors and Van Siggas just accumulate during this process.
Yes, you keep track of the total scaling applied to each row and column. For numerical stability, they mention accumulating these scales in the log domain. The final matrix has balanced standard deviations, and you have the corresponding vector dollars that achieve this transformation.
It sounds very efficient. No complex solvers, just iterative division.
Extremely fast, as the results show later. It converges typically in very few iterations.
Now, this choice of metric, imbalance, is interesting. The paper contrasts it with kurtosis. Other work suggested minimizing kurtosis might make weights easier to quantize. Why does SINQ argue imbalance is better here?
This is a really key point they make with experimental data. Kurtosis measures the tailedness of a distribution. Lower kurtosis means fewer extreme values, which sounds good for quantization, and you can optimize kurtosis directly. But when they tried minimizing kurtosis directly in the context of their dual scaling approach, they found it actually increased the matrix imbalance significantly.
So making the overall distribution shape nicer in terms of kurtosis actually made the variance across rows and columns less balanced.
Exactly. It seems that forcing low kurtosis might create local pockets of high variance that the dual scales then struggle to manage. And because the dual scaling relies on balancing variance between rows and columns, a high imbalance leads to poor results.
So the empirical result was minimize imbalance leads to low imbalance, low kurtosis, and good perplexity. Minimized kurtosis leads to low kurtosis, high imbalance, and bad perplexity.
That's what their figure 2 shows, yes.
Yeah.
For this dual scaling transformation, minimizing the variance imbalance, IW ballers, seems to be a much more effective proxy target for achieving good end-to-end quantization performance than directly targeting kurtosis. Internal variance consistency matters more than the overall distribution shape.
Okay, so we have the transformation. Now, how does it play with others? Can you combine SINQ with techniques like activation-aware quantization, AWQ?
Yes, you can, and they call this combination ASINQ, but the order matters a lot.
Why is that? What is AWQ doing fundamentally?
AWQ looks at the input activations, as well as the weights. It tries to find scaling factors for the weights such that the output error, considering the activation magnitudes, is minimized. It essentially scales down weights that are multiplied by small activations and scales up weights multiplied by large activations.
That's data-dependent calibration, finding scales alpha based on activation statistics.
Correct. Now, if you just take your original weights, apply AWQ to get WEQ, and then feed WEQ into the EWQ algorithm.
The Sinkhorn iterations will just normalize away the AWQ scales.
Pretty much. The AWQ iterations are designed to force all row-column standard deviations towards, it doesn't care why the variances are what they are, it will just normalize them. So it would undo the careful scaling done by AWQ.
So the correct order must be SINQ first, then AWQ.
Exactly. The AWQ procedure is, 1, take the original weights to dollars, run the SINQ algorithm, algorithm 1, to get the normalized matrix HAST full in D2, then apply the AWQ scaling to HATA 3. Finally, quantize the result.
And the AWQ scales then get absorbed into the final SINQ scales.
Yes, the AW scales can just be multiplied into, say, the vexa vector without needing extra parameters. This way, you get the benefit of SINQ's variance normalization and AWQ's activation-aware importance scaling.
Clever. Okay, what about inference speed? We talked about the dual scales, vex and meritive vex. Does applying both slow down the matrix, multiply in practice?
That's another crucial practical point. If you had to fully reconstruct the weight matrix, weight per box, vex-vec before the multiplication, it would add overhead.
Right, dequantizing would be more complex.
But they show you don't need to do that, especially with the common 1D tiling approach where vex is a full column vector. Let's look at the linear layer calculation.
Okay.
XAA, vex-vex.
Okay.
You can rewrite sexticket vex odot q plus vex using the properties of matrix multiplication and element-wise products. Turns out you can compute sexx q plus vex first.
Which is just the standard quantized matrix multiply with Roblox scales and shifts.
Exactly. And then you take the resulting output activation vector and apply the column scale vec to it with a single element-wise multiplication.
Ah, so the second scale vec just becomes an extra scaling step on the output activations, not on the weights themselves during the main multiply.
Precisely. This means the forward pass complexity is very similar to methods like AWQ, which also often have a scale applied to the output. It adds just one cheap element-wise vector operation per linear layer. Minimal inference overhead.
That's really elegant. It keeps the core matmul efficient. Okay, so considering all this, how does SINQ fit into the whole landscape of PTQ methods?
Well, within uncalibrated uniform methods, it's a clear advancement over basic RTN, round to nearest. It's different from HQQ, which optimizes shifts based on error norms. It's conceptually related to Hadamard transforms that also try to normalize weights. But SINQ is architecture agnostic and doesn't rely on specific layer structures or dependencies, which is a big plus.
And it's compatible with other approaches.
Yes, that's key. It's orthogonal to non-uniform quantization. You can run SINQ transformation first, then quantize the result using NF4, for example. They show results for SINQ, NF4.
Okay.
And it's also orthogonal to calibration. As we just discussed with SINQ, you can combine it with methods like AWQ. So it's really a flexible pre-processing step that improves the weights before you apply your chosen quantizer, whether it's simple uniform INT4, non-uniform NF4, or a calibrated method.
All right, theory and implementation sound promising. Let's get to the bottom line, the results. How does SINQ actually perform, starting with the main claim, uncalibrated uniform quantization?
Looking at tables 1 and 2 in the paper, the performance uplift is pretty dramatic, especially at 4-bit and 3-bit. They test across the Quint3 family, 1.7B, 14B, 32B parameters.
And compared to RTN, Hadamard plus RTN, HQQ.
SINQ consistently comes out on top in every single uncalibrated case they show. The improvements aren't trivial either.
Can you give an example?
Sure. Take Qwen3 1.7b at 4 bits. The baseline RTN gets a Wikitext 2 perplexity, lower is better, of 18.74. HQQ improved that a bit to 18.00. SINQ gets it down to 17.12.
That's a significant jump at these low bit levels.
It really is. They mentioned that in several cases, SINQ cuts the gap between the quantized model and the original 16-bit model by more than half. It's retaining much more of the original quality. The gains are even more stark at 3-bit, where methods like RTN really struggle.
Okay, perplexity is one thing. What about other quality metrics? They looked at flip rates, too. Why are those important?
Flip rates are arguably more revealing for tasks that require reasoning or factual recall, like question answering. Perplexity is an average over language modeling, but a flip rate measures how often the quantized model's output sequence differs from the full precision model sequence.
So it catches cases where one wrong token choice derails the whole answer.
Exactly. A small change in perplexity might hide a significant increase in these critical errors. So looking at Table 2 for Qwen3 32b at 4 bits.
The big model.
Right. RTN has an average flip rate of 5.26%. SINQ drops that down to 3.6%. That's a big reduction in output divergence.
How does that compare to non-uniform, like NF4?
Interestingly, the BitSandbytes NF4 implementation, B&B, had a flip rate of 3.99% in their tests. So SINQ, using simple uniform INT4, actually had fewer output flips than the non-uniform NF4 approach on this large model.
Wow. That suggests the normalization is really preserving the model's behavior effectively.
It strongly suggests that, yes, maintaining that structural integrity seems to be a key benefit.
Does SINQ hold up on even larger or more diverse architectures? They tested MOE models, too.
They did. Table 3 includes results on Qwen3 235b A22b and MOE model, and DeepSeek v2.5-236b, which uses different attention mechanisms.
Yeah, that's generalized.
It seems to. The results show it performs robustly. For instance, on the huge DeepSeek model at 4-bit, SINQ achieves the best perplexity of 5.48, just edging out RTN at 5.49. While the gap is smaller there, it demonstrates the method remains stable and effective even at massive scale and with architectural variations. It's not brittle.
Okay, now for the combinations. We talked about orthogonality. Does combining SINQ with NF4 or AWQ actually help in practice?
Yes, the results show benefits, with one really interesting finding. Let's look at Table 4, combining with non-uniform NF4. SINQ NF4 generally improves over just using NF4 alone.
So the normalization helps even before applying NF4. Makes sense.
But look at the Qwen3 32b results again. Plain SINQ using uniform INT4 achieves 7.74 ppl. SINQ combined with NF4 got 7.83 ppl.
Wait, the uniform version beat the non-uniform version in that case?
Slightly, yes. That's a fascinating result. It implies that once SINQ does its job normalizing the variance so well, the added complexity of non-uniform quantization like NF4 might not provide any further benefit and could even introduce a tiny bit of noise or approximation error. The normalization itself was powerful enough.
That really underscores the effectiveness of the transformation. What about adding calibration with ASINQ?
Table 5 shows ASINQ plus AWQ. As expected, adding AWQ calibration on top of ASINQ gives a further boost over uncalibrated SINQ.
And compared to other calibrated methods?
For the Qwen3 1.7b 4-bit case they show, 8NNQ outperforms standard AWQ, GPTQ, and even Hadamard plus GPTQ. So it seems SINQ provides a better starting point for calibration methods like AWQ to build upon.
Okay, the quality story is strong, uncalibrated state-of-the-art, good combinations. But the other major selling point was speed. How fast is the SINQ quantization process itself?
This is maybe the most compelling practical advantage. Table 7 and Figure 5 show the quantization times, normalized relative to the fastest baseline, RTN.
And SINQ's time.
It's incredibly close to RTN. On average, it takes only 1.09 times longer than RTN. For the 32B model, it was about 51 seconds versus 47 seconds for RTN. The overhead of the Sinkhorn iterations is almost negligible.
Wow. Compare that 1.09x factor to the competition.
It blows them away. HQQ was over 2x RTN time. AWQ, which is considered efficient for a calibration method, was over 30x RTN time. And GPTQ was over 60x RTN time.
So SINQ gives you near AWQ, or sometimes better quality, but at basically RTN speed for the quantization step itself.
Exactly. That's a massive difference for anyone needing to quantize models frequently or quickly.
And even ASINQ, the calibrated version.
Still very fast compared to other calibrated methods. It clocked in at about 8.5x RTN time. Way faster than AWQ's 30x or GPTQ 60x. So if you need calibration, ASINQ is a much faster route to high quality.
Okay, wrapping up the results, any key takeaways from ablations or architecture points?
The ablations in Figure 4 basically confirmed their default choices were good. Using 1D tiling with shifts seems slightly better or equivalent to 2D tiling, and the precision of the auxiliary scales didn't matter much. The main thing is the method's robustness and lack of interlayer dependencies, unlike something like Hadamard transforms. That makes it easier to apply to new unseen architectures. It's genuinely architecture agnostic.
Okay, let's pull this all together then. SINQ seems like a really significant step forward for practical LLM quantization.
I think so. It cleverly sidesteps the slowness and data dependency of calibration by focusing on transforming the weights themselves.
Using those three core ideas we discussed.
Right.
The dual scaling parameterization giving extra flexibility.
Right, the Watt prox vec vet form.
The matrix imbalance metric as a target, focusing on variance uniformity.
Sigma max, sigma insective.
And that fast, iterative, Sinkhorn-style algorithm to actually minimize the imbalance efficiently.
Yeah, the alternating normalization of row and column standard deviation.
And the result seems to be state-of-the-art quality for calibration-free, uniform PTQ, especially at 4 and 3 bits, rivaling much more complex methods.
And crucially, doing it with near-zero quantization time overhead compared to the absolutely simplest baseline, RTN. Plus the minimal inference overhead we talked about.
The performance seems consistent, too, across different model families like Qwen 3, Llama, DeepSeek, and various sizes.
That robustness is key. It really suggests that this approach of carefully normalizing the weight distribution before quantization is fundamentally sound and broadly applicable.
Which brings us to our final thought for you, our listeners. Given how well SINQ performs achieving top-tier results with a fast, uncalibrated, uniform method by focusing purely on a clever weight transformation, does this signal a potential shift?
Should future research maybe double down on finding even more sophisticated yet efficient weight space transformations like this? Transformations that inherently make weights easier to quantize, reducing the reliance on slow, data-hungry calibration procedures, or complex non-uniform formats that can add inference cost.
SINQ proves that mathematical elegance applied directly to the weights can be incredibly powerful and efficient. Perhaps the next big leap in low-bit quantization lies not just in better calibration or new number formats, but in finding even smarter ways to precondition the weights themselves.
It certainly makes a strong case for that direction. Something to think about.